Now that we have visually talked about symmetries and the meaning of even and oddness for a function, let's go ahead and turn our attention to an algebraic test. The two remaining symmetries, so we have the origin and we have the y-axis, right? Do you guys recall how we algebraically tested for these two types of symmetries? Right? So go back to the memory banks and let me go ahead and right? So for the y-axis, what we did is we took the point xy and we replaced it, with negative xy. So we left the y alone, but replaced the x with its opposite. And then the idea is we got the same equation. If we did, then we knew we were symmetric with the y-axis. For the origin, what we did is we took our point xy and we replaced both of them, all right, with a negative and got the same equation back. So that's what we did back, I think it was in 2.1 when we first investigated this. But now, right, we are talking about functions. So we're no longer calling y y, right? Y is f of x. So how do we do what we did here in a functional language or function notation? Well, the easier of the two is this guy, right? Because what we're basically saying is that the function value at negative x, right, has to be the same as the function value at positive x. So again, let's look at that visually. So if I have a function, the classic one is x squared, right? Here's negative x and here's x, and they basically both have the same output. So the function output at negative x is the same as the function output of positive x. And so you can see, right, the input has changed. We went from positive input to a negative input, but the output has stayed the same. The y value at negative x is the same as the y value at positive x. So there is how we functionally look for that. We replace x with negative x, do the math, and if we get f of x back, then we are basically going to be an even function, right? Because we're symmetric about the y-axis. Now this one's a little harder, right? Because they're both changing. And so what's going to happen, let me go ahead and just show you the notation and then we'll talk about it. But picture-wise, right, let's just have a graph that's nice and symmetric. We have x comma y and then negative x, negative comma y over here. So it all begins with replacing our f with negative x. But there's got to be also a negative in front of the y. So there's a couple of ways that we can do this, and I actually think one way to do that is to, the way the book wants you to do it is they put the negative right here. So this is your negative y, and that is your negative x. So in the equation, I have both, right? I've replaced x with negative x, and I replaced y with negative y. For me, what I like to do is I like to put the negatives on the both sides. So for me, I like to think of it as negative, let me write that better. So f of negative x, if I negate that, what we get is the function back. And so there's my double negatives here. There's a negative in the input, and there's a negative on the output. If these double negatives create our function back, then we are basically symmetric about the origin and we are odd. So you do what you want to do. Again, this is what the book is showing you, but I think in practice, if you divide both sides by -1, this is f of x, and that's negative f of negative x. So what it all is about, right, is replacing the input and getting the function back even. I'm replacing the input and the output with their negatives and getting the function back, and then that means I'm symmetric and I'm odd. Odd means there's a double negative, even means there's just one negative. So obviously what we now have to do, now that we've developed some tests, we need to go practice them to see who's even and odd. And then we can always use our graphing calculators to kind of check to see if we're right. All right, but we're 5 minutes into this, so let me go ahead and stop here, and we'll try our algebra test in a moment.